Thanks to have invited me here. I will talk about the splitting methods that are numerical integrators that are designed for contact Hamiltonian systems. So numerical methods that will preserve the structure structure friendly. The talk will be divided in two parts. In the first part, we see the theoretical basics of the construction, while in the second part we will see some numerical examples. So let's start from the arena of the contact dynamical system that are the contact manifold. We will consider exact contact manifold. So a contact manifold in which we define the contact distribution through the contact one form. And the contact one form gives rise to a volume form on the whole contact manifold. When we have chosen an eta, a contact form, we can also associate to it a unique vector field called Reb that describes the complemental distribution to the contact distribution. So we can define what we are going to study. So the contact Hamiltonian system that are really similar to the symplectic ones. We start from the definition of an Hamiltonian, a real function, and we induce an Hamiltonian vector field, which construction is really similar to the symplectic case. In red are enlightened the differences between the symplectic case and the contact case. We show that the existence of an equation, a new equation, that is the first equation which describes the projection on eta, and while in the second equation we have an additional term due to the contact structure. In coordinates, we can see also this difference. In particular, we have an additional term in equation for the time evolution of the momenta. In particular, that is associated. We associate it to a damping or a forcing, more usual to a damping. While we have an extra equation more that is related to the additional dimension due to the contact structure. In particular, we have that the Hamiltonian vector fields are infinitesimal contactomorphism. So the flow generated by this Hamiltonian vector field will preserve the structure. We will describe some particular systems that usually are in this form, in which we have a kinetic term, a potential term, and a damping that will depend on the extra variable. Which type of system we can describe? First of all, we have the damped harmonic oscillator that we have already seen during this conference, but we can also describe something more complicated as a modifying Kepler problem, a two-body problem where we add a sort of periodic external force that depends on the velocities of the reduced problem. We can study the Lane-Dennheim equation that is not a dynamical equation, but it describes the density of an autogravitating gas that is in equilibrium. Or we can also study the van der Pol system, so the prototype of the nonlinear oscillators. In order to build up these integrators, the first ingredient is the Jacobi structure that we have naturally beyond any contact manifold. That is a Lie algebra structure on the function defined on the manifold. That is a construction really similar to the Poisson brackets. We define it through a QB vector field that is strictly related with the contact distribution and by the Reb vector field. The properties are the bilinearity, the skew symmetry, the Jacobi property, since we have a Jacobi structure, but we don't have anymore the Leibniz rule, but we have a generalized Leibniz rule that involves the supports of the function. But the most interesting property is the relation between the Jacobi structure, so the Jacobi bracket and the Lie brackets that are defined on the tangent bundle, that permits to use the Baker-Campbell-Hausdorff formula, and in particular to study the solution to equation 9 for Z and give some important properties. If we consider equation 9 in which x and y are two vector fields, in particular Hamiltonian vector fields in contact setting, we can also argue that Z will be an Hamiltonian vector field if the series in 10 will converge, but it's not assured. So let's go to the integrator. So we want to integrate a differential equation that usually we see in 11. To any differential equation, we will have a formal solution that can be replaced with the solution in closed form when we have it. In particular, we want to have it in our case, but we will see it later. So we define a numerical integrator of order n. We call a numerical integrator of order n if the distance, the error made at each step is of order tau at n power, where tau is the step of the integrator. How we can define the contact Hamiltonian splitting methods? We have to consider a Hamiltonian dynamical system that gives rise from an Hamiltonian function. We want that this Hamiltonian function can be expressed as a sum of different terms, in this case we call small hi. And in particular, we want that each of these Hamiltonian vector fields of these parts of the Hamiltonian vector field is exactly integrable. So we can found to this differential equation in 14 the exact solution. Since we have the exact solution, we can also say that the equation 15 is a second order integrator and is in particular our second order integrator that will preserve the contact structure. While we can also build up the same integrators when we have a time-dependent Hamiltonian just by the adding of two terms, one at the start, one at the end, that represents our time translation. This symmetry that we are trying to preserve inside the integrator is due to maintain the order 2. The order 2. So by this second order integrator, we can also build up in two different ways some higher order integrator. The first way is with an iterative method in which we define the integrator of order 2n plus 2 from the order 2n, but this definition will involve some parameters, some coefficients that in this case can be exactly found by an algebraic equation. The second way is a composition method in which we define the integrator of order 2n by directly by the application of the second order integrator. In this case, unfortunately, the coefficients that are involved are not exact, since the algebraic equation that gives they are not solvable. For this reason, we need some numerical methods also to solve these algebraic equations. And in particular, if we consider the sixth order integrator, we will find three different set of coefficients that are A, B, and C in the table. And if we observe it, they are really different one to the other. In fact, the coefficient A will consider just the smaller step than B and C due to the values of these coefficients. Which are the features? we have a composition of exponential map that are Hamiltonian. That means that from the Baker-Campbell-Hausdorff formula, we have that also our integrator is an Hamiltonian flow. This means that we can found an Hamiltonian, and in particular, we have a sort of modified Hamiltonian that will describe the system that we are integrating with our method, and not anymore the original system. And this modified Hamiltonian can be studied in order to see the error or other feature of the new system. Third property, we have that on the long integration, we have a sort of stability that we will see in particular when we consider the Kepler problem. Let's go to the examples. The first example, first the implementation, sorry. So we have already said that we have this Hamiltonian that will be split into the kinetic term, the potential term, and the sort of the damping term. And in particular, we choose this combination of terms that are from 18 to 20. The first example now is the Lane-Emden equation that is a static equation that describes the density of an autogravitating gas that is in equilibrium. In particular, the quantity Q is this density, and the T represents the distance from the center. We can found an Hamiltonian that is, for some magic reason, a sort of kinetic term plus potential term plus damping. And why we consider this type of system? Because first of all, we have a singularity in the differential equation due to the singularity of t at the start of the integration. And in order to avoid this numerical problem, many numerical methods that are use neural networks or other types of integrator will fail. Secondly, we have exact solution for this equation with particular value of n, in particular 0, 1, and 5, that will help us in order to study the approximation of the error. These are the integration with our method, with the second order integrator. And we will see that also if we have a bigger time step that is enlightened with the dotted line, we have a good behavior. But let's go to the error estimation and how to see if our integration is good. We want to consider once again the second order integrator, and we use the Baker-Campbell-Hausdorff formula in order to have a unique exponential map. In this way, we can reconstruct a modified Hamiltonian, and that will be a sort of Hamiltonian with one parameter more that will be the time step. This modified Hamiltonian can be computed explicitly when we have this splitting, and at a fixed when we fix an order that we need, we have considered just the first order correction, so the tau at second power. And we can compute both the modified Hamiltonian for the time independence situation and the time independent situation. What is needed in order to have the errors estimation is this theorem that gives us the possibility to compute the local error, so not the global error on the whole integration, but just at each step. And it's what we have made in the following slides. We have the integration of the Lane-Emden equation with n equal to 0. So we have the exact solution, and we compare the error that we made effectively with the exact solution and what we can compute with the modified Hamiltonian. And we see that in this case, this the modified Hamiltonian gives us an upper bound, also for n equal to 1 and n equal to 5. The next example is the modified Kepler, that is the two-body problem with external perturbation that will depend on the velocity. We have chosen a perturbation that is periodic and will have a sort of frequency. What we can see, the first thing is that the stability is more stable than Runge-Kutta 4, and Runge-Kutta 4 is a fourth order integrator, while our Hamiltonian second order is a second order integrator. We can also study the error of the method, and we see that in this case the approximation is not so good as before, but we have many reasons in order to explain that. The first thing is that we don't have the exact solution of the modified Kepler the modified Kepler problem, so we have used the Hamiltonian at the sixth order in order to have a numerical error. And secondly, we have used the local error and not the global error, so it can be failed to be an upper bound. The approximation are better if we have a bigger eccentricity. We don't have any explanation about that, but it happens. Secondly, we have that as other type of splitting methods, we have the traditional drag of the orbits also in this case. Now we can study the difference between A, B, and C. So the three types of coefficient that we can choose for the sixth order integrator with inexact coefficients. We choose to study the inexact coefficients because our computation, the inexact coefficient method is computational better and has less cost than the exact coefficient method for the higher order integrators, involve less calculations. So these are the plots with different tau. Is a little bit confusing, but what we can see from a rapid look is that as we argued before, the coefficient size are better than the other, and also that with a small time step, these orbits will be pretty the same. Last example is the van der Pol oscillator. That is the prototype of nonlinear oscillator, in which the nonlinearity is parameterized by the parameter epsilon. In this, we have some difference in this case between the cases before. First of all, our contact Hamiltonian is not anymore in the form of a kinetic term plus a potential term plus the contact damping, but we have a sort of singular Hamiltonian since we have a sort of linearity in the momenta. In fact, this case is strange since from equation 32 we see that the momental is taken by the s variable, while in these cases the p variable play the role of the extra dimension of the contact case in a strange way, which is the main feature of the van der Pol oscillator is the limit cycle that appears. And our integrators preserves this limit cycle also for really big time steps, as we can see. But there are some strange behaviors, in particular the born of these tails when the time step is with a particular dimension. These tails are more evident when we study big nonlinearity. In fact, they arise before, and it can be studied on this plot on these plots. In particular, we see how they play an interesting role when the time step is bigger with respect to the nonlinearity. In particular, the last picture, the first picture of the last line. Since we have a periodic orbit, we can study also the period of this periodic limit cycle, and we have studied with the modified Hamiltonian with using the perturbation method, and we can study this perturbation method till the sixth order. After it becomes really computationally expensive, also for Mathematica and other symbolic tools. And we can approximate this period of the limit cycle in a good way. So this is the essential bibliography. We have started from the construction of higher order simplicity integrators that are the cousins of these contact integrators. And thanks for the attention.